Welcome to our exploration of phase transitions in physics, where we dive into the mathematical frameworks that help us understand how materials change their state. Today, we'll focus on two influential theories, Landau theory and Bragg-Williams theory. These approaches provide deep insights into the behavior of systems near critical points, such as when a material transitions from disordered to ordered states. We'll break down key concepts, equations, and the physical meaning behind them, making complex ideas accessible and engaging. Let's begin by setting the stage for why phase transitions matter and how these theories revolutionized our understanding. Landau theory offers a powerful mathematical framework for describing phase transitions, especially near the critical temperature, often denoted as Tc. The theory introduces the concept of an order parameter, which quantifies the degree of order in a system. When the system is disordered, the order parameter is 0. As it becomes ordered, the parameter takes on a non-zero value. This approach allows physicists to model how materials behave as they approach and cross the critical threshold, providing a foundation for understanding complex phenomena in condensed matter physics. Order parameter, often represented by the Greek letter phi, is a central concept in Landau theory. It serves as a measurable quantity that distinguishes between the disordered and ordered phases of a system. Near the critical temperature, phi is assumed to be small and uniform, simplifying the analysis. This parameter helps scientists track how a system evolves as it undergoes a phase transition, making it easier to predict and understand changes in physical properties. By focusing on phi, Landau theory provides a clear lens through which to view the transition process. Key feature of Landau theory is the expansion of free energy density as a power series in the order parameter. The equation Ft, phi equals a half R phi2 W phi3 plus a phi4 captures how the free energy changes with phi. Each term in this series has a specific role. The quadratic term relates to stability, the cubic term can introduce asymmetry, and the quartic term ensures the energy remains bounded. This mathematical structure allows physicists to analyze the stability and behavior of systems near phase transitions, offering a versatile tool for theoretical predictions. For a system to reach equilibrium and remain stable, Landau theory requires that the highest order term in the free energy expansion be even with a positive coefficient. In our equation, the quartic term of phi4 must have u greater than 0. This condition prevents the free energy from diverging and ensures the system's physical behavior is realistic. By enforcing stability, Landau theory provides a reliable framework for predicting how materials respond near critical points, making it a cornerstone in the study of phase transitions. Interestingly, if we remove the odd-order terms, such as the cubic phi3 term, the Landau free energy expression aligns with the Bragg-Williams theory. This connection highlights how different theoretical approaches can converge, offering similar descriptions of phase transitions under certain conditions. It also demonstrates the versatility of Landau theory, which can be adapted to match other models by adjusting its mathematical structure. Understanding these links helps us appreciate the broader landscape of physics theories. Bragg-Williams theory is a mean field approach commonly used to study magnetic systems, especially within the Ising model. This theory simplifies the complex interactions between particles by considering average effects, making it easier to analyze large systems. By focusing on mean values, Bragg-Williams theory provides a practical way to explore how magnetic materials behave, particularly as they undergo phase transition. Its application to the Ising model has made it a fundamental tool in statistical physics. Bragg-Williams theory, free energy is defined using the thermodynamic relation F equals ETS, where E is the internal energy, T is the temperature, and S is the entropy. This equation captures the balance between energy and disorder in a system, providing a foundation for understanding how materials respond to changes in temperature and other conditions. By analyzing free energy, physicists can predict the stability and behavior of magnetic systems, making this relation central to the theory. Within the Ising model, the order parameter is the average spin. Denoted as m, this quantity measures the net magnetization of the system, distinguishing between ordered and disordered magnetic states. By tracking m, Bragg-Williams theory provides a clear way to analyze how magnetic materials transition between phases. The average spin serves as a bridge between microscopic interactions and macroscopic properties, making it a key variable in the study of magnetism. Bragg-Williams theory introduces several important variables. N is the total number of spins, n up arrow is the number of up spins, and n down arrow is the number of down spins. Total spins are given by n equals n up arrow plus n down arrow, and the average spin m is calculated as n up arrow n down arrow. And these relationships allow physicists to quantify the state of the system and derive further equations, such as 2n up arrow equals n plus nm, which connects the number of up spins to the average spin. This mathematical structure is essential for analyzing phase transitions in magnetic material. Mean field approach of Bragg-Williams theory simplifies the complex interactions in a system by averaging them. Instead of tracking every individual particle, the theory considers the overall effect, making calculations more manageable. This method is particularly useful for large systems, where direct analysis would be too complicated. By focusing on mean values, Bragg-Williams theory provides practical insights into the behavior of magnetic materials and their phase transition. The order parameter varies across space. Landau theory incorporates a gradient term into the free energy expansion. This term, proportional to the square of the gradient phi2, accounts for spatial changes in the system. Including this term is crucial when variations are significant, as it allows the theory to model non-uniform behavior. However, if changes are slow on a microscopic scale, these spatial variations can be neglected, simplifying the analysis. This flexibility makes Landau theory adaptable to different physical scenarios. Inclusion of spatial variation terms in the free energy expansion is vital for accurately modeling systems where the order parameter is not uniform. These terms help capture phenomena such as domain formation and interface behavior, which are common in real materials. By considering spatial gradients, physicists can better predict how systems evolve, especially near phase boundaries. This approach enhances the realism and predictive power of theoretical model. Landau and Bragg-Williams theories both provide frameworks for understanding phase transitions, but they differ in their approaches. Landau theory uses a power series expansion and focuses on the order parameter's behavior near critical points, while Bragg-Williams employs a mean field perspective, simplifying interactions by averaging. Despite these differences, both theories offer valuable insights and can be connected under certain conditions. Comparing them helps us appreciate the diversity and depth of theoretical physics. Wrap up, we've explored how Landau and Bragg-Williams theories describe phase transitions, each offering unique perspectives and tools. Landau theory's power series expansion and focus on stability provide a detailed view of critical phenomena, while Bragg-Williams' mean field approach simplifies analysis for large systems. Understanding the order parameter, free energy, and spatial variations is essential for predicting material behavior. These theories form the backbone of modern physics, guiding research and innovation in condensed matter and beyond.